Hey everybody, it's Dr. Vaccaro here. I wanted to take a little bit of time and go through the vacuum plugin. So a number of students have contacted me and asked me a little bit about if I could meet with them and talk through the process of getting through vacuum. So I wanted to take a moment and break this down into a couple of different pieces. And what we see on the screen is a representation, like I say, of a sort of stylized version of a mini Moog, an actual synthesizer that was manufactured for the 1960s and 1970s. It went out of production for a number of years. Then it came back as something called the Mini Moog Voyager, which was a more modern take on it with MIDI implementation. A few years ago, they sunsetted that project and they brought back a modern Mini Moog, or a non-Voyager Mini Moog. So these are actual hardware synths that are currently in production. This plugin is meant to be evocative of that, but that's not truly what it is. It's just the kind of framework that we are looking at. And the couple of things that I want to bring up about the Mini Moog is that it was a performance synthesizer. There are two categories of synthesizers, what we call modular synthesizers and what we traditionally called performance synths. Modular synthesizers were made of a whole bunch of individual modules that were loaded into a case. And to connect them, you had to physically patch cables from outputs to inputs from those various modules to create your synthesizer patch. It's the source of the terminology patch when we talk about that being a particular sound, is that you had to patch the cables in the right way to get that sound. That took a little bit of time to patch all of those cables in. And in a performance situation, that wasn't always practical. So the idea of a synth that didn't require manual patching to change all of the configurations, that had a simplified architecture, but one that could rapidly be re-changed to create sounds for different songs in a live performance. So in other words, we tend to think of these as giving up a little bit of the sonic flexibility from something like a modular synthesizer, like a Moog modular, or a plugin like the Arturia Moog modular, or we think of like a Mini Moog as being sort of the simplified, we give up some of the flexibility, but what we get in return is a little quicker and easier interface to get around on. So as we talked about in class, synthesis involves a couple of things. We're going to have tone generators. These we call oscillators, and in the case of the vacuum plugin, they occur over here in the upper left quadrant. So we see VTO1, VTO2. These are the virtual oscillators that are running in this plugin. Next to that, we have a mixer, and the top part is the main thing I want to draw our attention to right now, because this is where we're going to change the balance between VTO1 and VTO2. So in its current configuration, we are only hearing VTO1. VTO2 is turned all the way down. And so any change that I make over here in the upper left segment is going to actually impact our tone. So if I change the range, for example, I can change the octave in which the tone is being generated. The terminology for this comes from pipe organs. So longer pipes have lower frequencies. So when we go down to the 32-foot pipe, we get very, very low tone. We go to 16, 8, 8, 4, 2. So that's how we set the initial range where we want our keyboard to operate. And part of the reason this was necessitated is that, as you see here, kind of the form factor on these keyboards were such that you didn't have a huge 88-key keyboard, a huge range to be able to play all of the different pitches you might want on one controller. So much like a modern MIDI controller, where we might only have a 25 or 49-key keyboard, it makes sense to try and set this up so that the range on the instrument fits within the range we're trying to control on our keyboard. So for the demo, I'm going to set this at, well, we'll set it at 16. That gives us a nice low frequency tone to sort of build from. All right, so I've cleaned up my session a little bit, and we've got a track now called Vacuum, and that's where we, of course, have the vacuum plugin we've been talking about. I also have, just as a comparison, I have a plugin by a company called Arturia called Modular version 3. This simulates a Moog modular. And again, in this case, this sort of looks like the form factor that we might expect for a cabinet, which has been populated with modules. And again, you can see that individual cables are being run from outputs of modules into inputs of other modules. And that's how the whole thing works. In the case of Mini version 3, this is Arturia's take on a Moog, on a Mini Moog. And again, you see a simpler form factor, no patch cables, an easier way to control the unit. So you see no patch cables, an easier way to control the unit. It's a far easier unit to use live. But again, for our assignment, we're focusing on vacuum. So we're going to hop back over here, and we're going to talk a little bit about the different waveforms that can be created in the oscillator. So we can see here we have triangle, sawtooth, pulse width 50, which is going to be a square wave, and then various other pulse widths that represent a change in the percentage of positive versus negative. So to get a sense of what this looks like, I actually want to record the audio from the output of each of these oscillators so that we can look at the waveform for it and get a sense of why these waveforms are called what they are. Then we're going to take a minute and we're going to look at them in various types of metering plugins that are various types of metering tools that will allow us to look at frequency spectrum and spectral envelopes. So we're going to take a moment and we're going to print some audio from this plugin. And the way I have this set up right now, I have an aux send going pre-fader on bus 1, 2 to the audio input on this track. I have it muted so that we're not hearing two of it. So I just want to play tones from the keyboard, and we're going to print these different waveforms and send them through. In the meantime, I am going to change the cutoffs on both these filters to reset them to their nominal positions, just so we get a better representation of this waveform. As I'm doing this, if you notice in the lower portion of the plugin, there's a little screen that shows the position of the knob if you want to get precise about your quantification. And in this case, I want to get precisely on triangle, sawtooth, and square wave, the three waveforms that are available with this oscillator. So we could hear the timbre change between those. Let's look at the waveform. So this was our triangle wave, and as we see on the screen, it's not a perfect triangle wave, but you do get the impression of a somewhat triangular shape. So this is our sawtooth wave, and you notice it is sort of shaped like a tooth of a blade. It keeps jumping back and sweeping down. And this is our square wave. Now we're seeing an imperfect square. Instead of these shapes transitioning perfectly as blocks, basically it's not perfectly jumping from one to the other. That's fine. In fact, that's because we're dealing with a less than perfect bandwidth in digital. But in any case, those are the three waveforms. So we are meaningfully seeing a difference in terms of what the waveforms for these different shapes look like. We have this squarish wave, and you can see why we call this a pulse width 50, because it's 50% of the time positive, 50% of the time negative. Then we repeat the cycle again, over and over. Here we have that sawtooth wave, which again, normally on paper, we would see it as going perfectly in a straight line. Again, this is an effect of the digital bandwidth. And then our triangular-ish wave. So that's where we get the name for those three waveforms. The big thing is they just sound different. So in our system at UMass Lowell of talking about timbre, the system created by Dr. Moylan, we identify four key characteristics that we want to talk about in terms of sound quality evaluation. So the first of these has to do with pitched versus non-pitched, noise-like versus pitched. So basically, noise-like sound tends to involve frequency content that spans the audible spectrum, and in any given period of time, the amount of energy that we would measure at any particular frequency has a relationship to the amount of energy in every other frequency. So for example, in white noise, which we can demo here, we are hearing all frequencies at roughly the same energy level in any given period of time. With pink noise, we shift that so that the energy is equal from octave to octave. The effect of this is that there's less energy in the high frequencies, because if we have the same amount of energy from 10K to 20K, as we do from 20 to 40, that's going to give us a meaningfully different result than if we have the same amount of energy between 10 and 10,000 or 10K and 10,000 20K as we do between 20 and 40. So here we go. Again, you'll hear this as having less energy in the high end. White noise, pink noise. When we talk about something as being noise-like, there's no pitch quality to it because all frequencies are represented equally. We don't hear a tone. We hear an overall sound quality, a bandwidth of sound. So one of the first questions that we want to think about in terms of sound quality evaluation is the quality of the sound and what component of it is noise-like, what component of it is tone-like or pitched. So we usually do this on a continuum. We don't get super fancy about this. You have numbers from 1 to 5. 1 would be like a pure sine wave, perfectly pitched. 5 would be one of the noise types that we just listened to a moment ago, pink noise or white noise. So one of the first things that we want to ask is overall, is it more like 5? Is it more like that noise, or is it more pitched? And one of the things we should remember is that sound changes over time. So normally when you guys are doing this for critical and analytical listening, you will do this with a timeline. So you can represent that maybe at the very beginning of the sound, it was very noise-like, and then as the sound went on, it became increasingly pitched. And you would map that out on your timeline. So in any case, that gives us the first criteria to talk about timbre. So the second criteria that we want to talk about is frequency spectrum, the frequency components that are actually present. Now, if something is noise-like, we're going to expect to have a lot of frequency components present. If something's pitched, we're going to expect to have primarily a limited number of tones, and we expect them to follow in some portion of the harmonic series. So we expect to see frequency components or partials that are whole number multiples of a fundamental. The next quality that we talk about has to do with the dynamic envelope of the sound overall, the amplitude changes that happen over time, and then we recognize that the frequency spectrum, each spectral component can have its own dynamic envelope. All right, So let's take a look at these waveforms on a spectrum analyzer. So what we're looking at here is the Isotope Insight plugin, and we are looking at the audible frequency range on the x-axis. That's from 20 hertz to 20 kilohertz. And on the y-axis, we're looking at the digital amplitude, going from 0 dB full scale down to, you can see it kind of rounds off around 100 and probably negative 125, 130 dB full scale. So as we look at our first waveform, this was our triangle wave, we're going to see our fundamental, and then we're going to see harmonics of that fundamental. So what we're seeing is the fundamental, the third harmonic, the fifth harmonic, the seventh harmonic, and so on with odd harmonics. And there's a very particular relationship with these. What we find is that they are inversely proportional to the square of their harmonic number. So when we go to 1/3, we're actually 1/9 of the value, or 1/9 of the amplitude that we were for the fundamental. When we go to the fifth harmonic, we are at 1/25. In other words, we get a pretty rapid roll-off of these harmonics. Which gives us a sense of a low frequency tone, and it's got harmonic spectrum, it's got content there, but it's not maybe as present in that mid and high frequency range as some of the other tones. So here's our sawtooth. So we see a very different pattern here. We are seeing harmonic series, but now we're seeing both odd and even harmonics. So with the triangle wave, we're only seeing the odd harmonics. Here we're seeing both odd and even. So let's take a look at our square wave. So we're seeing that same pattern as we saw with the triangle wave. We're only seeing odd harmonics, but the odd harmonics are rolling off much less rapidly. In fact, we find here they're rolling off in a relationship that's inversely proportional to their harmonic number, rather than the triangle, which is inversely proportional to the square of the harmonic number. So again, here's our square wave. Here's our triangle. So one of the things that we're finding is that in the raw material, the building blocks that we're going to use in this plugin, there already are some pretty significant timbral differences between the three waveforms that first oscillator is capable of generating. The square wave and the sawtooth have harmonic content at a higher amplitude than the triangle wave. But all of them are complex waveforms. They all generate sounds that have both a fundamental as well as elements of the harmonic series. So let's take a look at oscillator 2. We see similar functions. We see that it has a sawtooth. It has a square wave generator, including the pulse width generator of various decreasing percentages. And in fact, let's take a moment and maybe print that. We didn't get a chance to see that. So as we look at the waveform, the first thing we should notice is it's becoming increasingly negative as we go on. We start to create a very, very different kind of look. So let's take a look. Here is our square-ish wave. Let's get out somewhere in here. Now you can see increasingly more and more of the waveform is in the positive portion. But oddly, what that ends up doing is shifting a lot of the energy so that we're getting a big amount of the amplitude in the negative in these downward pulls right there. And again, we got a pretty big timbral difference as it did that. Listen again. And let's maybe take a look at that in Insight. Let's look at the spectrum of that. So let's go back and let's look at VTO2. So again, we have our square wave generators. We have a sawtooth, but instead of a triangle, now we have a noise generator. So I'm going to turn down the output of VTO1. I'm going to turn up the output of VTO2. And now we can hear the noise. You notice because noise has equal content in all frequencies, we aren't really getting a difference from range. Once I get to the sawtooth, that works as anticipated. Okay, so that gets us through the core of the oscillators, the two things that we're using most frequently, which is setting the range and setting the waveform for those oscillators. So let's talk for a minute about how we might use those two together to create some more rich spectral content. One of the ways that we could play with more interesting harmonic relationships and even initiating pitches that were not necessarily related to the original harmonic series would be to play with these two oscillators. So let's look at what might happen if we put them both in the same octave and we give them different waveforms. Maybe a square wave and a sawtooth. So you can see we start to shift the harmonic spectrum a little bit. We start bringing in some of those odd harmonics, or some of those even harmonics rather, from the sawtooth as I turn this up. And we start to get some interactions between the odd harmonics that are coming from those. Now, let's see what happens if we take one of these down an octave. So we're getting a much more complex relationship. If you think this one through, we've gone down the octave, and you might think, hey, they're going to share the same harmonic spectrum. Sort of, but things are offset by an octave at this point. So we start getting into the point where the intervals between those harmonics starts getting smaller and smaller. And because of that, that's going to start to change things. So we get a much more interesting tone. Let's try and go the other way. Let's make it higher this time. So basically that's some of the core ways that we might think about combining these together, is that we're basically creating more complex timbres by introducing various harmonics in various octaves. So that last example is a nice point to segue into the next portion of things that I want to talk about here. And we'll come back and talk about a few other things, but I want to get through the core functionality of the plugin first. So the next thing we want to think about are the two filters. We have a high pass filter, which is going to filter out low frequencies. So as I change the cutoff, that's going to sweep the frequency of the border of the pass band into the higher frequency range. So watch what happens. So that allows me to take out low frequency content. I have a low pass filter. Again, these are named for the pass band, not what's being filtered out by but what's being allowed to pass through. So these two filters allow me to subtract or to take away harmonic elements that I didn't really want there. So we call this approach subtractive synthesis because we're going to start by generating a complex waveform using our oscillators, and then we're going to go back and we're going to filter out elements that we don't want. So that last example that we've been listening to for the last few moments presented an interesting quandary in that, like, as we had VCO1, we were starting with a relatively high-pitched kind of lead tone. When I brought in the second oscillator, because it's tuned way lower, we actually shifted the fundamental of this. And it became more of a bass tone. So one of the ways that we could solve that is by using the high-pass filter. So now we're getting the change in timbre without the change in pitch. And of course, this is a voltage-controlled high-pass filter, so as I change the control signal from the keyboard controller, that's changing the actual corner frequency so that it will track to whatever note I'm playing. Resonance is going to add a resonant peak. So if we imagine the shape of a filter, we might think about something like the McDSP plugin, which will show us this visually. So this gives us a frequency spectrum, and we see a low-pass filter here on the left. As I sweep it around, it allows me to set the corner frequency. I can set the dB per octave that the filter rolls off. And then I can add a resonant peak. In this plugin, it's called peak. In the plugin we've been looking at, it's called resonance. So as the filter becomes resonant, we get this bump that happens in the frequency immediately above the corner frequency. And you can, in fact, see at this point when I've made this incredibly resonant, it's actually the corner frequency is ending up in the positive compared to the pass band. But this gives you an idea of what a resonant peak is going to do. Resonant peak, for example, might allow me to bring back in a little bit of the fundamental we lost from that high pass filter. So we get a little closer back to the tone that we originally had. Let me pull up. And now you see really the impact of having the harmonics starting to stack up from a very, very low tone down here with a pitch that primarily has its fundamental up here. We start getting a pretty complex tone that has a lot of pitch elements that were not there originally. Again, we can use the high pass filter or the low pass filter rather the same way. And we can change the slope of that filter. Again, this is decibel per octave. So you can really hear the effect of that resonant peak. In fact, a lot of us, when we're going to be doing dynamically changing or modulating filters, enjoy having that resonant peak because we get a little more of that sense of the filter sweep. We get a little more of that kind of thing that, you know, it's the cool thing you do filter sweeps for. And we set the key tracking on this, by the way, using the key tracking knob here in the lower right of each of these. So now we've got a tone. Again, we could play with this in any number of ways. Maybe I decide I want to have less of those odd harmonics, or even harmonics rather. So right now my tone is kind of just sitting there. It starts when I play the keyboard note and goes until I release it. It doesn't have a very long release tail, and there's no dynamic change at all. So let's take a moment and talk through the envelopes. So these are the two modules here in the middle on the lower side right below the filters. And we have two of these envelopes. We can use them for various things. So let's take a moment and explore envelope 2 because this is the one that's going to be the primary generator for the dynamic envelope for the timbre that we have. So let's say I want to have a slower attack. So now I've got a nice slow onset, and let's say I want a decay time that's maybe a little faster, but we can't really hear that yet because right now the sustain level is 100%. So let's pull that back a little bit. Maybe not quite that much. So now that AD burst followed by a decrease in level for the sustain level gives me a sense of an articulation at the beginning of this tone. And if we jump over to a different view in this plugin, we can actually see a bit of how that's going to work. So with that slow attack, decay, sustain, we can see the slow increase and then it rolls back down. By the way, this is the time domain going right to left and frequency spectrum going away from us. So let me pull the sustain down even more. So now we can really see how each frequency spectrum component is given the same ADSR curve. Now, let's play with that a little bit. Let's go with an attack or a faster attack. So we can see the difference that that attack time is making in terms of that initial shape. And the decay time will again play into that. So let's say we want a very aggressive spike at the beginning. We might go. We might go with a fairly short time like that. And let's say I want a bit more of a release trail. Well, I can crank that up. So now we can see that release is happening after I let the key go, and it gives me a little bit of a decay time on that. So let's maybe so you can get a sense that that shape is now there. It's a little bit harder to see because we don't have as big of a difference between the attack portion, the attack level, and the sustain level. But that gives us our main overall envelope for the sound that we're playing with. And we do have an option here to make this velocity sensitive. So instead of No matter how hard I change, it doesn't change the loudness at all. Now, the velocity from my MIDI keyboard or from my MIDI programming is actually going to change the amplitude of the waveform. So that takes us through envelope 2. We're going to pause and come back on envelope 1 in a minute because it's a bit more multi-purpose. So let's finish our way through the rest of the architecture in the upper portion of this. So the next module over we have is an age module. This allows us to simulate some of the less than desirable effects of older synthesizers that have started to kind of break down. So one of the tendencies is that the oscillators may drift a little bit. So they've given us an oscillator drift knob here. At the extreme, it becomes almost unusable. When we take the drift all the way down to 0, it's like we have a perfect oscillator that doesn't have any drift at all. They also give us a dust element. All right, so in the upper right, we have our master volume control for the plugin in the VTA module. And we also have an extra control down here. I've been ignoring all of these controls related to saturation. We'll come back and talk about those in a minute. But again, this is going to set the overall volume output for the plugin. And of course, typically after I get a sound design and I'm pretty happy with it, I'll adjust that until I'm coming in right around my reference level. At this point, I believe my color break is actually happening at negative 18 dB full scale. So this gives us quite a few tools to shape a particular timbre. And again, these are very operational. We're talking about things that are actually changing waveform elements. But at a certain point, we need to recognize we're picking these things and designing these sounds based on the idea of being musically expressive. So let's talk about a few other ways that we can modulate or change our tone. So one of the other features they give us in the mixer section is instead of summing the tones, we can take these two oscillator outputs and we can multiply them together. The effect is called ring modulation, and we control that down here. Let's get rid of our filters here. We also have some features built into this based on the idea that they are simulating tubes. So the VTO1 and VTO2 stand for vacuum tube 1 and vacuum tube oscillator 2. So the idea is that they're not just simulating an analog solid state circuit, they're trying to simulate an analog tube circuit. And because of that, they give us the luxury of being able to add some overdrive to it, which is again going to increase harmonic content, but it's going to actually add harmonics for every harmonic. So I'm going to take VTO2 out. I'm going to take the ring mod out. We're just hearing our triangle wave right now. Let's switch back over to our spectral graph. So each harmonic generated by the oscillator is now generating its own harmonic series based on the overdrive. So what initially starts as just a subtle boost of even harmonics, making this a bit more sawtooth-like, at a key point, we hit a point where it goes into harmonic distortion, and we start seeing a lot of other harmonics being introduced. And again, we get a very different timbre. We also have the option to add saturation to any of our filters. Now, there are some signal flow considerations in terms of where we add that saturation. If we are adding that saturation in the mixer, which occurs before the filters, those are then going to get filtered out by the voltage-controlled filters. If we add them after the filters, then those harmonics are still going to be present. So that with even a very complex tone, we could easily overdo it. So, long story short, we have way more harmonic distortion available to us in this plugin than we would even need. The last place we want to look is on the final output amplifier, because this gives us a choice of adding how much of that we want to add to our actual sound. So let's look at a bit more sophisticated way that we might use these filters. So one of the things that can happen with real-world tones is that we can have a different spectral envelope for different frequency components. Now, we're somewhat limited in the way that we can do that within a subtractive synthesis architecture, but we do have the ability to use one of our envelopes, envelope 1, to control the cutoff frequencies of our filters. So let's take a tone that I've thrown together here. And let's pull the low pass filter down. To the point that it's actually pretty far down, and I want to push maybe the resonance up a little bit, because I want to make this move. So now I'm going to tell envelope 1 with this lower envelope 1 knob right here. I'm going to set envelope 1 to a significant amount of control on this filter. So now envelope 1 is actually going to change the cutoff frequency of this filter. If I want that to be a slower sweep, I can put a longer decay time. And again, I can use all of the standard features. Now I can even make this velocity sensitive, which will change exactly how much of the filter is happening depending on the velocity level. So that gives me the ability to make these filters really dynamic, to make them a key aspect of musicality. We've talked about this idea that as performance intensity increases, timbre should change. Well, one of the ways that we can build that into a basic performance patch is by using envelope 1 to control these filters. We could play the other direction as we go down with the envelope 1 knob. It actually starts to have the opposite effect. So let's turn that back up. Let's play around with the high pass filter and do the same thing on that. So we've got this right now with no velocity. Let's turn it up and give you a little velocity demo here. So now we're getting a pretty significant difference in timbre just by playing with velocity. So that takes us through all of the controls on the filters. Again, we've got our saturation, we've got our key tracking, which determines whether the filters move with our control frequency. We have the cutoff and resonance, and then we have the slope or decay of the filter. So let's hit a few other features here. One of the other things that we might decide to do is to subtly detune the oscillators. So we find that each oscillator has its own fine tuning. Now, one of the reasons we might do that is to create like a chorusing effect. If we have two oscillators that are very close to in tune but not quite, gives us a slightly more interesting tone. But we can do the same thing with the octave offsets. Now we're getting really complex tones because we're not getting anything close to the original sound we were playing with. We can also use envelope 1 to control the shape function on here. Let's take out the other oscillator. Let's get rid of velocity, actually. Let's bring in the other oscillator. So finally, we haven't really talked about noise yet, but we could begin to add noise-like components to our sound. To add a very quick noise-like component to the beginning of our signal. One thing to note, if I don't let the release time run its sound all the way through, it doesn't let me add a new ADS portion. So we get a nice legato sound. That's one of the ways that we can actually play with. That release portion. And again, simulate a bit more of a legato touch. So a few last functions that we want to talk about are some of the ways that we might want to route various other aspects, various control signals around within these synthesizer modules. And the routing portion of that is going to happen on the lower right side over here. So we have two knobs that allow us to set sources. One of them picks a source of envelope 1. So its voltage change over time, correlating to the ADS-R curve. Envelope 2, the virtual tube oscillator or the vacuum tube oscillator 1 or oscillator 2. In other words, the oscillators can be used to modulate or change other signals. So, for example, let's say I wanted to take out VTO1 or VTO2 as a tone, but maybe I wanted to use it to control some other aspect. Or maybe we want to change the shape. Or we want to change one of the filters. Now, because I have this in the lowest register, we are down below the audible range. So it changes very much in that range versus even in the lowest register. Pretty different tone. So again, one of the interesting things we can do. So on the lower knob, we have as a source the low frequency oscillator, the LFO, which is this portion down here. We'll come to that in a moment. We have mod wheel, MW, which is this controller here. This is controlled with a CC assignment for mod wheel. You may have a modulation wheel on your MIDI controller. I do. A combination of the LFO and mod wheel And finally, AT, which stands for aftertouch. Not all MIDI controllers support aftertouch, but aftertouch allows you to change the pressure on the key after you have played the note and allow that to impact things. To be honest, I don't know if my MIDI controller does. Let's try it. Does not seem to. I am on a fairly cheap M-Audio controller right now, not one of my nicest MIDI controllers. So let's maybe go to the mod wheel on this and see if we can make this do some interesting things for us. So what that's now doing is it's using the mod wheel as the source to control how much of the signal is modulating VTO pitch. And we could do that with filters. So finally, the LFO, which we've mentioned a few times, is this oscillator down here. A low frequency oscillator happens below the range of human hearing. So we go from just above 0 hertz to 20 hertz. So we could use that to control a lot of things. For example, let's say we wanted vibrato. We could have the low frequency oscillator change the pitch. Seems a bit aggressive, but maybe we just want to have it change the VTO pitch. So we wanted to have a bit more control over that, so we're going to use that and bolt the mod wheel. So that gives us a nice vibrato effect. We could also, of course, have that LFO changing any of these other addressable parameters here. So that gives us some control routing that we lost when we went to this type of mini performance synthesizer. So over here we see the LFO and the destination assignment that works directly with the mod wheel, which is its normal operation. So that gives us separate control over how we would use this LFO modulator. So the final feature that I want to look at is an arpeggiator. It's not going to be useful for the Debussy assignment, but it is an essential part of a synthesizer. It's a way of basically having it play repeated notes in a pattern without having to play that actual note pattern. So if we turn the arpeggiator on and I just play a note, we get a rapid rearticulation, and how fast it rearticulates is set with the rate. Now, where this gets interesting is if I hold down more than one key at the same time. Now, the shape that it's going to be playing those notes is going to be determined by the mode right here. So when I hold down 3 notes, C, D, and E, we hear the scale degree 1, 2, and 3. If I go to down, U and D is up and down, and then random. So where this starts to get really interesting is when we play bigger and bigger groups of notes. So that gives me a chance to kind of create that kind of that rapid arpeggiating pattern. So, kind of a fun way to generate interesting repeated chord patterns. I'll turn that off because it's not much use for us for this assignment. So that, I think, goes through pretty much everything that you've got here that you're going to want to play around with. All of these aspects are automatable. So by default, I think as we found, one of my MIDI knobs is controlling the A and D, and then over here, the S and R. The other knobs are controlling the other envelope. So that gives us the ability to control that. Again, in this plugin, if we right click, we can find the existing CC, MIDI CC value, that we need to automate to control that parameter. If there isn't one set, for example, here, we can just say learn MIDI CC, and I'll turn a knob on my controller, and then that one will be controlled by it. So from there, we can implement any kind of automation that we want to from Pro Tools. So let's go into Edit View and maybe take a look at this vacuum track. So if I go down into the MIDI portion here, I can address any of the individual controllers. So if I want to write automation for the modulation wheel, it is set to mod wheel 1. Let's say over the course of these MIDI notes, I want to have the mod wheel move between a couple of positions, or maybe I want to be able to draw a bit of a shape. So we can see the mod wheel on the plugin is moving. So that gives me the ability to modify and to automate any of those parameters. But remember, like modulating or changing the modulation wheel doesn't inherently change the sound unless you have the mod wheel actually doing something meaningful. So for example, let's route that. Let's maybe get a sound that is a bit more effective for this. So now, because the modulation wheel is controlling the low pass filter, we can hear that changing. Again, let's get rid of this waveform because that's not at all what we're seeing right now. That just happens to have a similar shape. But I could equally have that changing pitch. Or I could have it set to vibrato. And again, any parameter here could conceivably be automated. So, for example, MIDI CC73 is controlling the A part of my envelope 2 ADSR curve. So I can go into controllers, go to add remove controllers, and I believe I said that was 73. So I'm going to go to the bank that includes 73, grab that one, add it, boom. Now I can change my attack time on each of those articulations. And again, we'll see this knob move. And we could change that in gradual steps. So again, that gives us the ability to control and automate any of these parameters here. If we can right click on it, if it's MIDI assignable, we should be able to assign a MIDI CC to it. And that gives us the ability to control and automate any of these aspects. So if I were working in this portion of my file where I have the Debussy, so let's get to a little more sane tone for this. Let's maybe undo some of that modulation. Or get that back under control in some way. So you get the idea. Now I can go through and modify any of those parameters over time. So let's say maybe early on I decide I want to change my attack, or I decide I want to change the cutoff for the filters, or I want to change the resonance over time. Any of those are parameters that I can now automate. But as you found, we don't really have to necessarily do a ton of automation if we've got our stuff set correctly. If we've gone through and got a sound that responds to velocity, I want to hear that last cutoff. So you get the idea. We can now go through and start to apply some musical intention to create the various timbres that we want to support our interpretation. And again, in an ideal world, you should be listening to a recording, comparing, hearing what that performer did, and trying to take elements away from that. In other words, what we want to do is take the best aspects of what real human beings do when they play acoustic instruments, and we want to learn to apply that as an expressive tool in what we have with an electronic instrument.